Hello everyone, today we'll talk about the problem count number of nice subarrays. We're given an array of integers and we want to count the number of subarrays, so contiguous portions of the array, that have exactly k odd numbers within them, and return that number. The first thing that we may do, which might make it easier to think about this problem, is that instead of having a1, a2, a3, we can transform our array into some binary array, with every value just being the remainder in division by 2, so essentially whether or not the corresponding number is odd or even. So that can either be modulo 2, that's the same thing as ending with a 1, because a binary end with a 1 only retains the least significant bit, which is exactly the bit that tells us whether or not the number is even or odd. And if we have this transformation, then we want exactly k ones within our array. So essentially we want the sum to be equal to k. So that's a standard problem. Maybe some of you already know how to solve it. And there are many solutions, many ideas. There are some ideas that are based on a sliding window technique, where we try to push the right and left end and make sure that we always look at arrays between right and left that have exactly k odd numbers. And then, so for instance, we have this array, we have I here, we have j here, we have k odds, so the sum is equal to k. And maybe this is an odd number, this is an odd number, this is an odd number, this is an odd number. So we have to add to the result every combination of I from this interval and j from this interval. So we're going to have to remember something along the way to make sure that, for instance, for every j that we look at, we add every possible I to the result, or vice versa. So that's one solution. I think it's pretty tricky to code compared to some other solutions. Another idea that's also very natural in problems like this is to use prefix sums, because if we want the sum to be equal to k, so let's say that here the sum is equal to k, then what is the sum here? Well, we don't know. We know that the sum is greater than or equal to k. And what is the sum here on this prefix? Well, it has to be the sum of this small correct array plus the sum of this has to be this total sum. So essentially we can iterate through the right end, and if the current sum is, let's say, k plus 7, then we want to add to the result the number of times that the prefix of our array had a sum of 7, because then the sum of the portion that would remain after we subtracted every possible smaller prefix with a sum 7 from our large prefix that we're looking at is a correct subarray with sum exactly k plus 7 minus 7, so exactly k. So that's another solution. I think it's very intuitive. However, it requires some linear amount of memory, because we have to, for every possible sum, remember the number of times we've seen it. And finally, there is a last trick that we can use, which I'm going to use in my solution. And that trick is just that if we are going to find the number of exactly, so there are k, so if the count, or in this case sum after this transformation, has to be equal to k, then we might as well, for instance, look at sum greater than equal to k, subtract sum greater than or equal to k plus 1. Same thing in the other direction, sum at most k minus sum at most k minus 1. So instead of counting exactly k, we might count up to k, or k or more. So that's a transformation that's often useful, and we might also use it in this problem. And finally, let's go to the example code. So we will be counting this variant. We count the number of subarrays that have at least k odds, and we have to subtract those that have at least k plus 1, because those are the bad subarrays, so they shouldn't be counted. And how do we count it? Well, we go in a way similar to a sliding window, where we take I and j, so left and right end. And we always move the right pointer to the right. So we add the next number, so 1 or 0, as I mentioned here, this is ending with 1, binary end, right? So we move it forward, and then for as long as we have at least k, so if this subarray is good, then we move the left end forward. And you have to count the number of arrays that are correct for that left end before we move it forward. And that means that, for instance, if this is, again, we have the same situation. Here we have I, here we have j. So how many subarrays are good? Well, starting with I, every subarray ending at j or later is good. So we have the length of our numbers minus j plus 1, because here we've increased j already. So all of those are good subarrays. And then we push I forward, adjusting our sum, and again, everything here is good. So this is the one idea how to do it with a sliding window and also using this useful trick.